Okay, so again, I'd like to welcome everybody for today's session. I'm going to start off. We can move to next. There we go. I'm going to start off. I will be talking about the first three bullet points there: the structural mechanics, the performance, and the multi-physics. And then I will pass over for the pre and post processing over to Mukund. So I just want to emphasize that this is going to be a fairly brief overview of the 613 release. There are a lot of features and development that we will not have time to talk about in today's session, but I do encourage you to take a look at the release manual, and we'll talk a little bit more of that at the end. Okay, so I'm going to start off with structural mechanics. And the first topic that we're going to be covering in structural mechanics are our particle methods. This currently encompasses both SPH and DEM. SPH was released a number of releases ago. It's the smooth particle hydrodynamics. And it's a particle method where the particles actually interact with each other through standard type constitutive laws. The design for, or the intent of SPH is for modeling continuums which are undergoing very large deformations. Fluids is one typical example, but can also be used for impact analysis and bird strike type simulations. As I said, SPH was released a few releases ago, but in 613 we enhanced the performance by allowing it to make use of parallel processors, and I'll talk about that a little bit later in the presentation. I do want to focus more on the DEM method. DEM, this is our first release of DEM in Abaqus Explicit. And DEM is actually for modeling interaction between what you typically think of as particles, sand, granular particles. And these particles only interact with each other through contact. You can see that in the schematic on the lower right-hand corner. We have two particles, and you can see that they just have springs and damping between them, whereas the SPH up top actually interacts through the constitutive law. So we can move to the simulation. So these are two animations that show typical type applications. The one on the top is SPH, and this is modeling just the sudden release of a volume of water. And you can see that the particles they tend to stick together, but they can break apart, just like you would see in a real scenario. The animation at the bottom is a DEM animation, and this is a simulation of some type of mixing procedure where you have these little particles of blue and white which are being mixed together by these two screws. So this would be some type of maybe pharmaceutical application. Okay, so on the next slide, I want to talk about XFEM. So XFEM is our extended finite element method. We've had XFEM in Abaqus Standard now for 4 or 5 releases, and we continue to enhance it. In 613, one of the major enhancements was the ability now to apply distributed pressure loads on the surface of an XFEM crack. So in case you don't know, XFEM is a technique by which you can model fracture through a model where the fracture does not have to follow one of the element boundaries. One of the advantages of XFEM is you do not require that the crack conform to the mesh. In previous versions of Abaqus, we could model fracture, but we couldn't apply any kind of distributed load to these newly created fracture surfaces. In 613, however, we do allow the application of a distributed pressure load to the new XFEM surfaces. So you can see the animation that's running down in the left-hand corner. This is a pressurized vessel with a small crack, and as the pressure increases, the pressure is working on that cracked surface, forcing it to open up. So this is really a type of generalized 3D pressure penetration capability, which is now available using the XFEM in Abaqus Standard. Okay, so we can move on to the next slide. We'll talk about general contact, focusing on Abaqus Standard. As Dale mentioned, I've been here for 15 years, and over those 15 years, contact has always been a heavy focus of Abaqus, and it continues to be. We continue to put out state-of-the-art leading technology in our contact. In a number of releases ago, we first introduced general contact in Abaqus Standard. It has been available in Abaqus Explicit for a longer period of time. And we've continued to enhance and add to the capabilities for general contact and standard. And in 6.13, the focus of the enhancement was allowing general contact for beams. We're focusing on edge-to-edge interactions as well as edge-to-surface interactions. And so for the beams, we have two major types of contact that we're supporting. One is where you have two beams just coming in contact on the exterior surfaces. This would be like in the picture that you see there on your lower left, where you have the two green beams hitting each other from the outside. But the other type of interaction we have is more like tube-in-tube type interaction. And again, you can see that in the lower left. If you see the one beam has a tube, there's a beam on the inside of it as well. And those two beams, this is a case where you have a beam inside of a tube. This is something we still support for our ITT formulations, but now we also support that with general contact. So we can go to the next slide, where we have just some examples showing some of the types of simulations you can do now with this new capability for beam contact. The animation that's running up in the upper right-hand corner is actually something from a customer. The animation, the lower animation both animations actually show a coil of beams inside a flexible tube. The one on the bottom is an earlier analysis where they had to model the interior coil using solid elements because we didn't support the contact with the beams. But now the analysis up top with the general contact with the beams, the same analysis can be done, but now with a smaller dimensional model, just given still a very good fidelity, but just at a much lower cost. The picture on the bottom right, with the picture of the guiding tube, is an example of a tube-to-tube contact. So this is just that outside tube is just a guide. This is a rolling process. This is there's a tube being pulled up along that big cylinder, and there's that guide on the inside, which is just guiding that. So it's very easy to set these models up now using the general contact. And the other pictures just show a variety of other types of what look like fairly simple simulations, but they're actually very sophisticated analysis and very complex contact interactions which have to be resolved. Okay, so the next contact feature is pressure-dependent penalty stiffness. The focus of this development was to help with situations where you have a general preloading on a structure where you have contact and you're deforming the structure, and then you're going to follow that by a perturbation step. So the example that we have here, the picture all the way on the left, is a deformed body after a general step that's been preloaded, and in the middle is showing a frequency analysis after the general step. And in previous versions of Abaqus, when you follow the perturbation step by general step, if any surface that were in contact in the perturbation step were assumed to be tied together. So so you can see that in the frequency analysis there, where the surfaces were in contact, the displacement between the surface and the body is fixed. In 6.13, we've added given you some flexibility by allowing you to specify a pressure limit. And the way this works is that in the frequency step, you can define a pressure threshold. If the contact pressure between the two bodies exceeds this threshold, then in the perturbation step, those two surfaces are tied together. But if the contact is below this threshold, then those two surfaces are free to move apart. So this is just it gives you a little bit of flexibility in modeling perturbation steps after a general nonlinear step. And so you can see that the two eigenmodes there at the center and on the right are significantly different because of the difference in the way the contact is handled in the frequency step. Okay, I want to move on to material modeling. Over the last couple of years, we've had a significant effort in our materials group to enhance our ability to model polymers especially. And to do this, we've introduced a new viscoelastic model that allows parallel networks of viscoelastic behaviors to be defined. These can also be joined with a hyperelastic and plastic definition, so we can have rate-dependent plasticity and viscoelasticity in the same material behavior. This model also now supports Mullen's effect, which is a type of damage. So this was put into Abaqus Standard in the last release, and now is also available in Abaqus Explicit. The target for these types of material models are shown in the test data, which is shown in the lower right-hand corner, where you show this is it's showing the sort of typical types of behaviors you see for large deformation of polymers. It's a very complex set of behaviors where you have a primary response, which is your sort of nonlinear elastic response, but we also have features such as hysteresis. When you unload the structure and reload it back up, it does not follow the same path. And also, when you completely unload the structure, you can get permanent set, which you can see down on the x-axis. So these new capabilities give you options and the capability to model very complex types of material behavior that you see that you actually see in real polymer models. The last bullet point there talks about a user-defined equation of state for Abaqus Explicit. So this is a new feature. This is allows you, if you have your own equation of state model that you want to put into an explicit simulation, this is an interface which allows you to do that. Okay, now we're going to move on to visualization of gravity waves using AQUA. AQUA is a specialized loading capability which is designed to help you model loads typically encountered by submerged or partially submerged structures. It's used heavily in the offshore industry. And one of the loads that we have for AQUA is gravity wave loading. So these are just as a structure sitting in the water and the waves go by, this tends to push the structure back and forth. In 613, we now allow you to visualize these waves during post-processing using a set of features that you put inside the input file. The visualization supports all types of waves that we have, the Stokes, Airy, gridded wave definition, also user wave definition. It also supports Abaqus Standard and Abaqus Explicit. So we can move on to the next slide, which is the visualization, which is actually an animation of one of these waves. And so you can see there on the left, you can define a set of visualization surface elements, which you identify in the input file as being visualization elements, and then Abaqus automatically computes the elevation that those surface elements would have based on your wave definition. So this does a number of things. This helps you verify that the wave definition that you think you're putting into the model is actually one that's being used by Abaqus, and it also helps you ensure that Abaqus is responding the way that you think it should be. So the animation on the right is showing you what was previously available because we didn't have you couldn't actually see the waves. So this should be quite a help for people who do these types of simulations. Okay, so the last thing I want to talk about in structural mechanics is the mesh refinement for cell. Cell is our coupled Euler Lagrangian capability, and this is available in Abaqus Explicit. In the previous release in 612, we had a new feature to allow you to refine the mesh based on a certain criterion, but the refinement was a single level of refinement. So a given element could be refined only once. We've enhanced this in 613 to allow multiple levels of refinement. So the animations you see in front of you right now they're simple analysis, but they actually illustrate the capability quite well. And it's just the Lagrangian cylinder which is falling into an Eulerian domain of water. And in the two cases, we have two different criteria which are being used to do the mesh refinement. On the left, we're just using contact criterion. So any place there's contact between the Lagrangian and Eulerian mesh, we're specifying multi-levels refinement. So if you look there, you can see that whenever the cylinder contacts the water, the mesh is refined, in this case, to three levels. So you get a fairly fine mesh refinement right around that contact area, but away from it, it's still a relatively coarse mesh. And the animation on the right, we're using volume fraction. So any place there's an interface between the water and air or water in the Lagrangian domain, we are refining the mesh. So we have a number of different criteria that you can use for having mesh refinement. And this enhancement is really designed because was put in place because these Eulerian meshes for the cell analysis, sometimes you tend to have fairly large, domains, and these are structured volumes. But a lot of times there's some areas where you need a refined mesh to capture the behavior. But away from these areas, you're better off you can get away with a coarser mesh. And just from a performance standpoint, this can be quite a benefit. Okay. So leaving the structural mechanics part, we'll move on to performance. Performance, again, is something that we focus on quite a bit. We attack performance from different from different ways. We address performance used by modifying databases. We try to enhance algorithms. We work with hardware. So the example that we have right up here is an enhancement for our linear dynamics. A number of years ago, we created a high-performance database for linear dynamics, and we've been migrating the existing linear dynamics features over to this database. In 6.13, we've moved over. We've now support our coupled structural acoustic modes using this SIM-based database. The example here, this benchmark example, is just an acoustic analysis, a coupled acoustic analysis of an engine cover model. In 6.12, this analysis is a frequency response. Took 1 hour and 3 minutes, and now with the SIM-based procedure, it's dropped down to 1 minute. So this is, almost all of our linear dynamics capability are now moved over to this SIM-based database, but we're still there's a few loose ends that we've been adding, and this is one of them. Okay, so another enhancement on the next page is enhancements we made to our AMS-based substructure generation capability. So AMS is a eigenvalue solution technique. It's a high performance. It's designed for very large models that have many, many modes that are being recovered. And we took this AMS eigensolver and we leveraged it for our substructure generation. Substructure generation is a technique where you can take a large complex model and retain a subset of the number of degrees of freedom in that model. It's a very effective way for building up built-up structures where you have many, many degrees of freedom, and you can reduce the model size quite a bit but still retain, the important mechanical response of the structure. But the substructure generation is actually a step, and for large models, it can actually be a fairly significant step. So the table up there shows some of the performance numbers for this new procedure. The model here is a fairly large engine block. It's got 13 million degrees of freedom. They're retaining about 1,200 nodes and keeping about 500 dynamic modes. So your substructure size is about 1,700 degrees of freedom. In 6.12, the procedure, there's two steps when you're including these dynamic modes. The first is the frequency step, followed by a substructure generate. In 6.12, using a conventional approach, this model took about 84 hours to run on this particular platform. In 6.13, the enhanced conventional, we did some work to improve our existing algorithms, and we're able to get that down to 23 hours. So we're about a 4 times speed up, and most of that came in the substructure generate step. But during this we also saw that we could leverage the AMS during the substructure generation. And you can see that this analysis that used to take 84 hours now takes about an hour and 42 minutes. It's a very significant decrease in wall clock time. And you can see that the substructures generate step now takes just over a minute, which is very significant. And again, I know that when we first showed these results in conference, that people didn't believe the numbers, but since have been brought over and now they're believers. It's a very significant speed up that we have right now. Okay, the next thing, as I mentioned, we focus not only on data structures and algorithms, but we also focus on hardware. And we have had an effort now for a couple of years to try to leverage the graphic boards that a lot of you have on your computers, these GPUs. And the idea here is to try to leverage hardware that you might already have on your machine to get some speed up. In the 612, we released the ability to use the GPUs for the direct symmetric solver, and in 613 we've enhanced that also to allow this to be used for unsymmetric solves. So the graph here shows two examples. One is Model 1 and Model 2. They're just generic examples. And in both cases, you're getting speed up. The first one, you're getting speed up of about 50%. And the second one, you're getting a speed up of about 30%. And so the advantage, so here it is, you're getting non-trivial speed up, and all you're doing is switching on and leveraging hardware that you already have on your machine. Okay, the next thing is large structure models. Models keep on getting bigger, and so we've had an effort driven largely by airframe modeling, but this actually benefits many industries. And this is to improve the processing time for input file for our batch pre-processing. And so the graph here shows, the pre-processing time for models of various size. So the purple line all the way on the right was pre-processing time for Abaqus 610EF, and all the way on the left, on the right, I'm sorry, the blue line is the results now for Abaqus 613. So you can see in 610EF, a model of about 25 million degrees of freedom was kind of pushing what we could do at the time. Took just under 2 hours. But now we're able to run models with well over 200 million degrees of freedom through pre. They are taken now in the order of 2 to 3 hours. So it's like an order of magnitude faster than it used to be. And so this is work that will continue, that will really enable you to keep increasing your model sizes. Okay, the last performance enhancement I want to talk about is SPH. I mentioned earlier that in 613 we are supporting now parallel computation for SPH. And so the example, the animation you see running here is a dipping analysis on a body in white. This is really designed to simulate the loads that a body in white would undergo as it's being dipped through a fluid. The pictures or the colors of those different cubes that you see in the SPH domain, those are the initial domain decomposition of the SPH elements. Just to give you some idea of how the particles move around. The domain decomposition is not static; it's fully dynamic. So as the analysis continues, we continually are reload or rebalancing the processors to try to enhance or to optimize the performance. And then you can see on the graph there, is just showing the speed up. So on 2 CPUs, this analysis took about 15 days, and if you ran it on a 128 processor, it gets done in about 17 hours. So it's a very good speed up, very, very good speed up on processors. Okay, so the last thing I want to talk about is some enhancements to multi-physics. The first one is enhancements to our electromagnetics capability. The EM went in 2 releases ago. 6.11 was our first release of our EM capability, and we've continued to work on it. The first enhancement is a new element topology, which is a wedge element. The wedge element is designed to help transition from TET to TET. This is especially helpful for EM models with conductors where you have something called a skin effect, where most of the electric field is concentrated on a thin part on the outside of the conductor. So in that region, you need a fairly fine mesh. But in the air and the interior, you can get away with a fairly coarse mesh of TET elements. So this element, and so you can see that picture in the circle. If you look closely, you can see there that there's a set of wedge elements in there which are used to model the outside of the conductor. We've also support permanent magnets. This is something which is quite helpful if you're doing motor simulations. And we also support linear and nonlinear BH curves for these materials. We support prescribed motion, which allows you to specify a motion of a conductor moving through an electric field. The target here is for types of induction heating simulation, where you have a workpiece which is moving through the electric field. This prescribed motion allows you to include an important convective term in the underlying field equations. And the last bullet point here talks about co-simulation between EM and structural procedures, and Abaqus Standard is now supported, as long as co-sim between EM and heat transfer, which on the next slide, we have an example of an induction heating problem, where you have a coil going around a cylindrical workpiece. And the thing is, as you run current through the coil, it heats up the workpiece. But as you heat up the workpiece, the EM properties of the material actually change. So you need to have this coupling between the two analyses. So you can do this with co-simulation between these two procedures. Where the coil is putting a joule heating load onto the workpiece. And then the workpiece the temperatures are going back and modifying the EM properties of the conductor. And my last slide is going to be on our CFD capabilities. We've had a native CFD capability in Abaqus now for a number of years. In our initial implementation of CFD, we had a transient solver, but there are some situations where you have a steady state solution you're trying to get. So the top animation there is the airflow over a blunt body, and then you can see as the flow continues, you eventually reach a steady state solution. So in 6.12, we introduced an implicit transient time stepping capability, which allowed you to get to steady state faster by taking larger time steps. But in 6.13, we've actually implemented a full-blown steady-state solver. So this will allow you to get to your steady-state solutions quicker. We've introduced a new element topology in CFD as well. This is a pyramid element, and this is designed for enhancing our TET to brick and TET to TET transitions. We leverage this not only in CFD here, but also in some of our V6 products, where we've introduced a new solver, a new mesher that's designed for hex-dominated meshes. To just, again, expand the scope of problems you can solve with CFD, we've introduced a couple new turbulence models. There's a fairly commonly used SST variant of the K omega turbulence model, as well as a new hybrid wall function technique, which is designed to reduce mesh dependency, to reduce the mesh dependency of a solution when you have turbulence. We've also introduced a CFD heat transfer capability. So this is a first step towards a fully integrated conjugate heat transfer capability inside of CFD. Currently, if you want to do a conjugate heat transfer analysis, you can do the CFD part in CFD and then use a COSIM to couple that with a heat transfer analysis in Abaqus Standard. Now we can do the heat transfer analysis in just the CFD in the CFD product, leveraging the high performance capabilities there. And then this is a first step towards a fully integrated pure CFD conjugate heat transfer solution, so you won't need COSIM. And the last animation there is an enhancement to the ALE mesh motion capability in CFD. The ALE is used for situations where you have a body moving through the CFD mesh. So this animation there just shows a cylinder inside an airflow. We've introduced a new implicit advection scheme that improves the ability improves the robustness of the ALE algorithm and allows for a larger deformation to occur. Okay, so that's it. With that, I'm going to pass it over to Mukund.
Thank you very much, Chris, and hello, everyone. I appreciate the opportunity to present to you the product update for Abaqus CAE and the viewer. Our last update, 6.12, was a strong release where we introduced many significant capabilities such as hybrid modeling, visualizing model data in the viewer, session persistence, etc. In 6.13, we've kind of built on top of that by enhancing some of those capabilities, but we've also targeted a bunch of high-priority requests for enhancements from our customers, and these enhancements span the entire product from modeling, including geometry creation and meshing, to post-processing. And along the way, we've also made some performance improvements to boot. So in the upcoming slides, I'll go over some of the key enhancements that we've made. The first one I'd like to talk about is model instancing. Recall, in the years past, up until 6.12, you could only create an assembly as a flat structure where you could only instantiate parts. Now in 6.13, I'm happy to say that you can also instantiate previously created assemblies. In other words, you can instantiate models, hence the name model instancing, and you can create a true assembly structure with a hierarchy. The models that you instantiate can contain any number of parts, and the part instances in those models can be dependent or independent, native, or can contain orphan meshes. Just as in the case of parts, the models too can be instantiated any number of times. So you can see here the Create Instant dialog box has an option to choose between parts or models that helps you build your assembly. And in the model tree on the right, you can see that it reflects the assembly hierarchy. And in the example, you will see that a particular model is being instantiated multiple times. The input file that gets generated from such models will be a single, probably large input file where all the child instances of all the model instances are written as a flat list of instances in a single star assembly block. The model level data such as mesh, materials, section assignments, stringers, etc. are carried into the main assembly, and also the materials defined in the subassembly model are also pulled in. When we bring in the materials, we prefix the material name to help you understand which subassembly those materials were brought in from. Similarly, the part level and engineering level features are also brought in. However, the history level features such as loads, boundary conditions, and engineering features are not brought in, and they need to be recreated in the newly created assembly. If you go to the next slide, Dale. Of course, you can see that this capability is useful in general, but it's particularly useful in the example that we've shown here, which is that of a conveyor belt which contains a series of repeated frames. So here you can see each frame being a subassembly in itself, and we've instantiated that frame multiple times to create the overall assembly hierarchy. I must also point out that any changes that you do to the base part of the base assembly that's been brought in to build up your assembly would get propagated automatically. Next slide. In the area of meshing, we've added a new command which is available in the Mesh Edit toolbox that allows you to copy shell meshes. With this, now you can copy any mesh, be it native or orphan mesh, to a target geometry. Actually, you can consider this tool as a tool to copy mesh patterns. The way this works is that you would have to specify points on one or more loops to define the mapping between the source and the target. The source and the target can be different, but they have to be topologically similar so that the mesh patterns that you copy make sense. This command is also applicable at the assembly level between part instances. So you can imagine this tool in cases where you want instances of the matching parts to have matching meshes. Finally, along with this tool, you can apply the mesh smoothing tool to fine-tune your mesh and make your copied mesh to reflect the kinds of similar mesh that you want. Next, please. We've enhanced the query tool to help you instantly find all the pieces of geometry in your model that are not yet associated with any elements. And as you do that, you can optionally highlight them and create a set. As you can imagine, this would be very useful in workflows where you're working with a lot of hybrid parts, where you would, as you've created geometry using the mesh to geometry tool, you would like to know which pieces of geometry have gotten created, and as you apply loads and boundary conditions, you want to identify which are the pieces of geometry that do not have a mesh associated with them. So it's very useful in those cases. Next. We've modified the verify mesh tool for better and consistent usability. Now you can specify more than one criteria at a time, and you can see all the entities that match that specific criteria or the various criteria. You couldn't do that in 612, where you had to specify one criteria at a time. We've used the same GUI framework in all the other areas as well. For example, if you use the node drag tool in the mesh edit toolkit, you will see that the same UI element is available as you see the failure criteria in the failure criteria dialog as you drag nodes to see the quality of the mesh around the drag node. Next. Among the geometry enhancements in 613, you will see that we've added an option to specify stitch tolerance and surface fitting tolerance. So this is particularly useful as you create geometry from elements, so that you can keep the option to stitch as a very last operation, knowing fully well that the stitch operation is perhaps one of the most expensive operations as you cobble together the geometry. We've also now added the ability for you to import part names from step files. This did not exist in 612. And we continue to enhance these scripting capabilities, and we've added methods via scripting to help you pick faces by curvature or faces using an angle, edges by angle, element faces by layers, element face, picking using face angles and limiting angles, etc. This is just a summary of many other enhancements we've made in the scripting area. Next. In 612, you could specify an XFEM-based crack propagation using VCCT. Now in 613, we've enhanced this capability by supporting the debond option to specify that the crack propagation may occur between two surfaces that are initially partially bonded. Along the way, we've enhanced the contact interaction property that defines the mechanical failure criteria by providing options to specify the type of VCCT analysis you want to do. We've enhanced the surface-to-surface interaction by allowing you to specify an initially bonded node set to the slave face. Prior to this, this was only enabled for cohesive behavior, and now this is available for fracture criteria as well. We now support the debond option for crack analysis, and this option activates the propagation of crack between two surfaces that are initially partially bonded. We've added a few history output variables to request data from your analysis, in addition to the field variables that were already available prior to 613. We've provided also solution control through linear scaling. For those of you who use VCCT, you may be familiar that for most crack propagation simulations using VCCT or enhanced VCCT, the deformations can be nearly linear up to the point of the onset of crack growth. Beyond this point, the analysis becomes very nonlinear. So in such cases, linear scaling can be used to effectively reduce the solution time to reach the onset of the crack growth. Next. As I mentioned, we've made some performance improvements along the way. A lot of it goes through resolving many of the problems that you've reported through our customer services. So you'll find performance improvements in when you write out large input files to remote drives. We've also made some speed up in importing large input files, and particular improvements you would see when you upgrade older databases, especially large databases that contain a lot of interactions. Next. In the area of post-processing, we've continued to enhance the linked viewport capability that we introduced in previous releases. We now have added 3 more options for you to control with linked viewports, namely rotation centers, viewport annotations, and view cuts. Using the option of rotation centers, you can now specify the view manipulation center on any one of the linked viewports. So for example, if you specify a rotation center on one of the viewports, it's applied to all the other linked viewports. And you can manipulate your views and synchronize them together. Of course, any of these options can be turned off at any time. Similarly, the viewport annotation options turned on one of the viewports are linked, and these are applied to all the other linked viewports as well. Likewise, if you've linked a bunch of viewports and you have created a new view cut, that view cut is copied on all the other linked viewports. The goal of these kinds of changes primarily is to minimize the drudgery of making repetitive changes in multiple viewports, and you can link multiple viewports and improve your overall productivity as you post-process your results. Next. In the area of composites, we've enhanced the material orientation plotting by adding the options for ply as well as layup. Recall in 6.12, in the viewer, we only displayed element orientations based on selected ply, and there was no option available to show the play-up orientations for a particular model. Now, in 6.13, we've added an option to help you visualize the orientation used for the layup as well. So we've added similar options in the results option dialog as well, so you can now transform the results in the layup orientation that's available. Of course, this is only applicable for composites. For other models, if you select the layup orientation, the display will use the material orientation only. Next. Up until 6.13, we did not have the ability to save color maps, especially for those of you who work with large assemblies, upwards of hundreds or so. And many of you have said that there are standardized ways of creating color. You have standardized ways of creating color maps for components and subcomponents in large assemblies. So as a result, if you modified a part or a subcomponent, you lost the color mapping. Now in 6.13, we've added the ability to retain these color mappings. So with this, you can write out an XML file that can be read into a subsequent session to retain the color maps. And these color maps are also saved in the MDB and the ODB file. I must point out that the color mapping can be used on any entities such as parts, instances, element set, materials, etc. And it's available both in CAE and the viewer. Next. In 6.12, recall we introduced the capability for you to view model data in the viewer. So for example, you could visualize loads and other predefined fields in the viewer. We've enhanced that in 6.13 and added support for visualizing boundary conditions as well. So the table on the right that you see lists all of the boundary conditions that we now support in 6.13. So for example, if you go into the viewer and select a model that you're trying to analyze, you can see the boundary conditions you can selectively and also see the individual components of the boundary conditions in the viewer. It's a really neat feature as you try to understand your loads and boundary conditions on your model. Next. So in summary, 6.13 also has been a strong release for us. We've added many capabilities with emphasis on modeling of assemblies, as I mentioned earlier in CAE. Chris talked about many of our exciting enhancements in the area of multiphysics, particularly in CFD, co-simulation, engineering mechanics, etc. We continue, as Chris mentioned, to invest in contact and have made many exciting enhancements in the area of contact and performance as well. We've made some significant improvements in the area of linear dynamics and batch preprocessor. In the interest of time, we've only highlighted a few of the enhancements that are available in 6.13. For details of any of these and other enhancements, they are available, of course, in the release notes.